Section 9.1 is about graphing equations in the form of y equals ax squared plus c. So to start, let's go over some vocabulary. A quadratic equation is a nonlinear, meaning not a line, a nonlinear function that can be written as y equals ax squared plus bx plus c, where a cannot equal 0, which is the standard form of the equation. So take a look at the equation, y equals ax squared plus bx plus c. The highest power is x squared. And again, a cannot equal 0 because if a was equal to 0, that would take out the x squared term, which would no longer make it quadratic. So a quadratic equation is when the highest power is 2, so like an x squared. So basically in this section, or more so in this chapter, we're going to be taking the equations that we were factoring from last chapter and now graphing them. Every quadratic function has a U-shaped graph called a parabola, which again is a U-shaped graph, and it's pronounced parabola, not parabola. So you'll see later in the notes these U-shaped graphs and how they are formed. And now on to parent quadratic functions. The most basic quadratic function in the family of quadratic functions, called the parent quadratic function, is y equals x squared. So this quadratic equation is stripped of all numbers. It's just strictly y equals x squared. The graph of y equals x squared is shown below. So as you can see here, we have that U-shaped parabola. And let's talk about some characteristics of these parabolas. The lowest or highest point of a parabola is called the vertex. So of the parent function y equals x squared, the vertex would be at 0, 0, the origin. The other characteristic that you need to point out is the line that passes through the vertex and divides the parabola into two symmetric parts is called the axis of symmetry. The axis of symmetry for the graph of y equals x squared, our parent function, is the y-axis, this red line right here. Because if I think about taking this parabola, folding this side onto this side, they would completely match up. Now remember, the equation for the y-axis is x equals 0. So as you are graphing these quadratic functions in this chapter, you will need to find the vertex of your parabolas and also the axis of symmetries for all of the parabolas. Let's see some examples. So here's example number 1. It says graph each equation on the same graph, then compare them. So we're going to graph y equals x squared, our parent function, y equals 2x squared, so we're going to take our parent function and multiply everything by 2, and then y equals negative 1/2 x squared. So we will be taking half of our parent function and making it negative, and then comparing how these two graphs are related to our parent function y equals x squared. And we'll just do these using t-charts. So to set up the t-chart, we're going to go from -2 to +2. And this is what I want you to do in your homework unless I otherwise tell you to do different numbers. So what we're going to do is take these x values from -2 to +2 and plug it into this equation. So remember, if I type in -2 squared into my calculator and I don't put parentheses around the negative and the 2, your calculator is not necessarily going to give you the right answer. So you're better off just doing these in your head. So -2 times -2 is 4. -1 times -1 is 1. 0 squared is 0. 1 squared is 1. And 2 squared is 4. So what we're going to do is now take these ordered pairs, remember these are now ordered pairs, and graph them on the graph over here. We're going to do this equation in black. So I took all those ordered pairs, and this would be those 5 points. And remember, I'm going to draw one nice, continuous, smooth line to connect those, resulting in a U-shaped parabola. And there you have it. There is our y equals x squared graph. Now we're going to go on to part B and graph y equals 2x squared. So what we can really do, thinking about the order of operations, we would square the number and then multiply by 2. So what we can do is take these answers and just multiply them all by 2. So let's set up the t-chart. We're going to do this one in red, so I've set it up from -2 to +2, just like I said before. And again, I'm going to take these numbers and then just double them, since I know I'm going to be squaring the number and then multiplying by 2. So I would get 8, 2, 0, 2, and 8 for this graph. Let's see what happens to the graph when I take those ordered pairs and graph them. So there are my 5 points, and again, I'm going to take one smooth continuous line and connect them to make our parabola. So you can see here our U-shape has gotten skinnier. By multiplying by 2, our U-shape has gotten skinnier since the numbers were getting bigger faster. Now for part C, we're going to take our x squared and then do half of it and then make them negative. So again, we can take these numbers from our original T-chart, we'll take half of each one of those and then make them negative. So our T-chart will look like this. Again, we'll go from -2 to +2. And once again, just to reiterate, we're going to take our y values that we got from our parent function, since we know we're going to square it, and then take half of that number and then make them negative. So for 4, for instance, half of that is 2, so I would have -2 as my answer. Half of 1 is 1/2, and then I would make that negative. Half of 0 is 0, so to make that negative, I would still just get 0. And then I would just basically repeat for the last 2. So let's graph that. So there's my 5 points in the blue, and now I'll connect them with one continuous smooth line to make my parabola. And there you have it. Notice that since I made it negative, it flipped my parent graph upside down, and also the 1/2 made it slightly fatter. So multiplying by a number bigger than 1 made it skinnier for the 2x squared, and then multiplying by 1/2 made it fatter for the 1/2 x squared. So let's compare these. I know we kind of already have, but let's put it in writing. First, note that all 3 graphs have the same vertex at 0, 0, and the same axis of symmetry, which is the y-axis, which remember the equation that represents the y-axis is x equals 0. Multiplying by 2 in part B made the graph skinnier than the parent function, the y equals x squared, and becoming skinnier is actually called a vertical stretch. Multiplying by 1/2 in part C made the graph fatter than the parent function, which is called a vertical compression, and the negative sign reflected it over the x-axis, which you guys can think of as flipped, but reflection is the more mathematical way to say that. Take special note of how I compared them. I identified the vertex of each, the axis of symmetry of each, and then compared what each part of each equation was doing to that parent function, which will be similar to what you have to do in your homework. In example 2, we're going to graph y equals x squared plus 2 and y equals x squared minus 6, and then compare them to the graph of y equals x squared. So basically, we're just taking our parent function, x squared, adding 2 to it on the outside and subtracting 6 on the outside to see what happens to our original parent function of y equals x squared. So let's start with y equals x squared and look at that t-chart again. So there's our t-chart for y equals x squared, the parent function, and the graph of y equals x squared, the parent function. Now let's get into the y equals x squared plus 2 and the y equals x squared minus 6. Again, I'm starting with the parent function because now I can just take my y values from the y equals x squared, add 2 to all of them, and then later subtract 6 from all of them. So we're going to do the first one, y equals x squared plus 2, in red. So let's set up that t-chart. As always, I went from -2 to +2, and again, I'm going to take the y equals x squared, my y terms from our original parent graph. I'm going to take each one of those y values, and I'm going to add 2 to them. So it would be 6, 3, 2, 3, and 6, because I just took each one of these y values and added 2 to them. So let's graph those points. So there's my 5 points, and now I'm going to connect them with one nice smooth curve to make our parabola. And there you have it. Notice that our graph did not get any skinnier. It basically just shifted up 2 units on the y-axis. Let's move on to y equals x squared minus 6. We'll do that in blue. Let's set up that t-chart. So once again, I went from -2 to +2. And just like we did for the y equals x squared plus 2, we're going to take our parent function, those values that we got, and this time we're going to take each of the y values and subtract 6 from them. So I would get -2, -5, -6, -5, -2. Again, I just took 4 minus 6 and got -2. 1 minus 6 got -5, so on and so forth. So now let's graph those points. And now we'll connect those 5 points with one nice continuous smooth line for our parabola. And as you can see here, our graph did not get any skinnier, just like we didn't get any skinnier for the red graph, the y equals x squared plus 2, but our vertex was shifted down 6 units. So let's compare these. Neither graph got any skinnier or fatter, so there were no vertical stretches or vertical compressions. It stayed exactly the same. The only thing that changed was adding 2 shifted it up 2 units, and subtracting 6 shifted it down 6 units. So let's write that out. So once again, adding 2 to the parent function made the vertex shift up 2 units to become 0, 2, as we saw in the red graph. Subtracting 6 to the parent function made the vertex shift down 6 units to become 0, negative 6, like we saw with the blue function. This is called a vertical shift. Whenever you add or subtract to the outside of the x squared, you're either shifting it up so many units or down so many units, changing your vertex. You'll see that in your homework, so make sure you're aware of that when you're trying to identify the vertex. However, by simply adding or subtracting something to the outside of the parent function, that does not change the axis of symmetry. Notice that all 3 of these graphs still have an axis of symmetry at x equals 0. So once again, a vertical shift does not change the axis of symmetry, and therefore these 3 graphs all have an axis of symmetry at x equals 0, otherwise known as the y-axis. Our last example is example 3, which asks us how would the graph of the function y equals x squared minus 3 be affected if the function were changed to y equals x squared minus 2. So notice that we start with our parent function and subtract 3, and now we're changing it to our parent function minus 2. This graph, y equals x squared minus 3, would have a vertex at 0, negative 3, because it would just be that parent function shifted down 3 units. The other one, y equals x squared minus 2, would have a vertex at 0, negative 2, since it would just be the parent function shifted down 2 units. So what the difference would be is I'm going from 0, negative 3 to 0, negative 2. So from this graph to this graph, I would just be shifting it up 1 unit. So once again, from y equals x squared minus 3 to y equals x squared minus 2, the graph would just be shifted up 1 unit from 0, negative 3 to 0, negative 2. That's it for this section. Make sure you jot down anything you didn't understand that we can cover in class before we move on, and we'll see you then.